Hello, everyone. I'm Robert Hazen. I'm a staff scientist at the Carnegie Institution for Science, its Earth and Planets Laboratory in Washington, D.C. And I'm delighted to be able to share with you today some ideas about the co-evolving geosphere and biosphere, aspects that are extremely important to astrobiology, thinking about the origin of life, the evolution of life, the future of life, both on Earth and other worlds. Now, you might say, well, what's this about a mineral evolution approach? What does that have to do with astrobiology? And what I would answer is that if you think about it, minerals are really critically important. Of course, we know they're important as raw materials for technology and agriculture. In fact, all life depends on minerals. We know that minerals preserve a record of planetary history, and that includes everything we know about the ancient biological evidence of Earth. And of course, minerals have laid the foundation for solid state chemistry, for physics, the periodic table, X-ray diffraction. Numerous Nobel Prizes have been awarded for work in mineralogy. So minerals are important. I mean, we can accept that. But in terms of astrobiology, it's not just the aesthetics and the scientific importance of minerals, it's the idea that minerals are time capsules. Singly, in combination, minerals are the oldest objects you can hold in your hands. They tell the stories of the origin and the evolution of planets and of life, because every specimen is a time capsule. It's information rich. It's just waiting to be opened, waiting to be read. Those stories are present in the minerals and in the rocks. So what I want to do today may seem like a little of an excursion from astrobiology, but it isn't, because we're going to be talking about deep time and how planets change. Now, the traditional way of thinking about minerals doesn't allow us to do that. So I'm going to start by reviewing mineral classification system, the official International Mineralogical Association system, which is based purely on idealized chemistry and physics. But I'm going to propose a complementary system of classification called an evolutionary system that looks at how minerals have changed on Earth and other worlds through more than 4.5 billion years of history. And in the process, I'm going to introduce opportunities offered by a new way of thinking about minerals, mineral informatics, which is critical to the study of astrobiology. So let's step back and think about this for a second. What are the objectives of a mineral classification system? What do we need a classification system anyway? And for any subject, whether it's mineralogy or astrophysics or botany or whatever, you need to have a classification system so that we can talk to each other. If I talk about diamond or quartz or calcite, you need to know what I'm talking about. And so we need to unambiguously describe and name things. But classification systems have a deeper purpose as well. Ideally, they play central roles in the discovery and the articulation of scientific theories. So in that sense, you can have multiple valid classification schemes. Each one of those can address a different theory or aspect of nature. And that's what I'm going to be doing today. So let's go back and look at those IMA protocols, the International Mineralogical Association, which is the official body that approves mineral species. And a species is defined as something that's a naturally occurring solid that has an idealized chemical composition and idealized structure. So here's a photograph of a quartz crystal. In the IMA scheme, it's pure SiO2, silicon dioxide. It has the idealized quartz structure. And every unique combination of a structure and an end-member composition is a species. Right now, there's more than 5,800 approved species, about 100 new species approved every year. And we've estimated that there may be another 3,000 to 4,000 species remaining to be discovered by normal techniques. Okay, so this idea, this classification system goes all the way back to James Dwight Dana, a Yale mineralogist in 1850. The third edition of his system was the first to use chemistry and structure as the basis for classifying minerals. Now, think about that. Idealized composition, idealized structure. What you're saying is you're using the minimum number of bits of information to distinguish diamond from quartz, from calcite, and so forth. And that's an incredibly useful, very streamlined system. This isn't going anywhere. This is going to be the major system for classifying minerals for decades, perhaps centuries to come, because it is ideally streamlined. But here is the caveat. If we want to understand the coevolution of Earth and life, then you need a system that incorporates changes of minerals through deep time, and that can't be done with the IMA system. Because the IMA system doesn't incorporate the parameter of time. Look at these different stages of Earth history. Planets are dynamic systems. Their histories are recorded in minerals. And if you have an evolutionary system that incorporates the parameter of time, then you can understand more about how planets change through time and how life and rocks coexist and how they co-evolve. Another reason why we might want a new classification system is deeply rooted back in Aristotle thousands of years ago, where Aristotle talked about natural kinds. Now, the concept of a natural kind is just that nature has certain groupings, that they're intrinsic to nature. A good example of this is the periodic table, where each of those chemical elements differs because it has an integral number of positive protons in the nucleus. Carbon is element 6. It has 6 positive protons, and that's different from any other chemical element, and it's a naturally derived definition of carbon as opposed to boron or nitrogen. So the idealized IMA species simply are not natural kinds because there's no such thing as pure SiO2 in an ideal crystal structure. There are always other factors involved, trace and minor elements and defects and so forth. So what we're proposing is a system where we think about natural kinds. And finally, if you do it this way, if you classify minerals in this new way, it offers opportunities to ask questions in a new way. How does life emerge from non-living worlds? Well, life emerges from geochemistry, and you have to understand the rocks and minerals to understand that. How did life evolve on Earth over 4 billion years? Well, the evolution, the mere process of evolution is preserved in fossils, which are preserved in rocks and minerals. We need to understand where those rocks and minerals came from. And just asking questions, are we alone in the cosmos? It is possible, and I'll propose this at the end of the talk, that minerals themselves create a planetary scale biosignature. So we're proposing a different classification system, and we're saying the primary tangible evidence we have for the earliest processes in the solar system, and that includes the origin and evolution of life, are these information-rich rocks and minerals, because every mineral specimen is a time capsule. It's sitting there, it's waiting to be opened, it's waiting to tell its story if we're open to these ideas. Now, the key to understanding the coevolution of Earth and life is an emerging field called mineral evolution. And what I want to do is take you sort of through the evolution of this idea of the concept of mineral evolution. It's in 3 different parts. Part 1 started in 2008 with the publication of this paper, Mineral Evolution. And it's a very qualitative story about how minerals have changed, diversified through 4.5 billion years of history. And let me take you through that story. So mineral evolution is the study of the changing diversity, the distribution of minerals as a consequence of evolving physical, chemical, and ultimately biological processes in planetary systems. We look at changes of the diversity, just the number and the kind of species, the relative abundances of those minerals. We look at compositional ranges, including trace and minor elements. We look at sizes and shapes, the morphology of minerals. These are all things that are not included in the IMA system. So far, we focused exclusively on near surface phases, phases that are accessible to study easily on Earth. They're things that are most likely to be observed on other planets and moons, and they're where you have direct interaction with biology. Now, you could extend ideas of mineral evolution to the deep interior, to the mantle, even to the core of a planet. We haven't done that. It's perfectly possible to do it, and maybe other people will follow up with it. Okay, we're astrobiologists, and so we think about biology, and I have to say that there has been some blowback in this use of the word evolution in the context of minerals. But I want to defend it because evolution has several meanings. The most basic is change over time. It's been used in all sorts of contexts for more than a century. The evolution of the igneous rocks is a famous book by Norman L. Bowen, which has influenced petrology. We talk about the evolution of stars, we talk about the evolution of planets, we talk about the evolution of meteorites, so all sorts of evolutionary contexts where we're talking about change over time. Now, when I use it, I also imply complexification. That is, through time, there's an increasing diversity, patterning, and actually quantitatively measured complexity of the structures and the compositions of minerals. Those increase. There's also the idea of congruency, that is, each stage of mineral evolution follows from the previous stages. It's a sequence, a logical sequence, but it is not this. Minerals do not evolve by Darwinian evolution. There's no common descent, so please erase this from your mind. This is not what we're talking about. Now, here's the soundbite. Minerals form through a combination of chemical, physical, and biological processes. And we can do this by looking at 10 stages of mineral evolution on Earth to understand these kinds of successive changes. Actually, there's an earlier stage. There's a stage 0, what we call the minerals. These are minerals that formed before our solar nebula, before the solar system was even imagined. And this includes a series of phases that form around stars. So old stars have atmospheres that include carbon and silicon and nitrogen and oxygen and other elements. And as those atmospheres expand and cool, you condense some very high temperature phases, about 20 different phases in all. They incorporate about 12 different common chemical elements that are in the atmospheres of these old stars. And the mineral evolution question can then be, how do you get from these 20 starting minerals, the minerals that have 12 essential elements, to what we see today, more than 5,800 known minerals with 72 different essential chemical elements? And so we talk about the 10 stages. The first one is the primary condensates in the earliest solar nebula, forming these little droplets called chondrules and CAIs and other sorts of refractory phases, about 90 different mineral species. All of these objects came together to form planetesimals, which were large enough to differentiate into a core and mantle. So you had new kinds of rocks. You also had aqueous alteration. You had thermal alteration and impact alteration, leading us up to about 300 mineral species. And these minerals fall to Earth and other terrestrial bodies all the time in the form of meteorites. This is kind of a baseline mineralogy, stage 2. Now we think if there's a dry world like the moon or Mercury, probably those same 300 minerals are the dominant ones on these dry worlds. And this may be the end point of moon and Mercury. However, if you have a wet planet, stage 3 leads to new minerals, hydroxides, clays, ices, other sorts of types of solid phases at or near the surface, which diversify up to about 450 mineral species. And we suspect that this is probably the endpoint for Mars. So our model is that Mars is very much a stage 3 planet in terms of its mineralogy. Earth is larger, and so you get partial melting of basalt. You form a new kind of magma called granite, silica rich, and also it can concentrate rare elements like lithium and boron, beryllium, cesium. That gets you up to about 1,000 different mineral species, many of which incorporate these rarer elements. And on Earth, we have even more fluid rock interaction, partial melting, fluid rock interactions because of subduction. Hundreds of millions of cubic kilometers of Earth's crust and upper mantle melt, are processed, leading to new kinds of volcanism, new kinds of rare metal deposits, sulfides and sulfosalt minerals, also high pressure minerals that are formed as mountain ranges are created and as high pressure minerals are brought to the surface. And so this gets us up to over 3,000 different mineral species now. So these 3,000 mineral species, purely physical and chemical processes, stages 1 through 5. But I've already said we have more than 5,800 mineral species today. And so how in the world is that possible? Well, it turns out the principal answer is life, because life is an incredible engine of producing mineral diversity. I find this fascinating because I've been interested in the origin of life, and minerals are often invoked in the origin of life as catalysts. They're reactants in those early reactions, there's templates, just protection at mineral surfaces of delicate organic molecules, and scaffolding. So minerals play all these roles in life's origin, but then once life originated, life played key roles in the origin of minerals. This is one of the fun aspects of the coevolution of the geosphere and biosphere. Stage 6, the anoxic Archean biosphere, when chemolitho-autotrophs were the primary organisms. We think that there were new ways of depositing minerals, such as iron oxides and carbonates and phosphates, but we don't think that there were a lot of new mineral species. So we're still stuck at around 3,000 mineral species in stage 6. The game changer is stage 7, that's oxygenic photosynthesis. And as soon as oxygen enters the atmosphere, you have a whole new set of chemical environments forming thousands of new oxide, hydroxide, carbonate minerals, weathered minerals at the surface of the planet. The planet rusts and turns red, and you also form hundreds of new minerals. Copper minerals, about 2/3 of all the known copper minerals, simply couldn't form without oxygen in the atmosphere. 90% of the uranium minerals can't form until you have oxygen in the atmosphere. And hundreds of other minerals of the redox sensitive elements, they simply will not form until you have photosynthesis and the production of oxygen. So biology played a huge role in that diversification. Stage 8 is the billion-year period known as the intermediate ocean, sometimes called the boring billion, when the oceans essentially were titrated. There's ferrous iron, which gradually gets converted as oxygenation of the ocean occurs from top to bottom. It takes a long time, but that's what happened. Stage 9 is snowball Earth, in these periods where you cycle back from the snowball Earth to the hothouse Earth. So during snowball Earth, the principal mineral species at Earth's surface is ice. And then during hothouse periods, it's possible that all the ice on Earth went extinct. So we're going cycling back and forth as Earth did during that 300 million year interval. And finally, stage 10, the Phanerozoic biomineralization of the last 500 million years or so. This gets us up to the complete inventory of 5,800 plus minerals. Lots of new biominerals and clays. We have shells, we have teeth, we have bones. Minerals, hundreds of them associated with coal deposits, taphonomic minerals, other minerals that form exclusively through biological processes. So biomineralization is an amazing engine for giving diverse minerals. And I have to tell you one story. This is just sort of an aside, but I'm fascinated by trilobites. And these trilobite eyes, these compound eyes, are amazing because every one of those little lenses is a single crystal of the mineral calcite, calcium carbonate, with the c-axis pointing straight out at you. But the trouble is, calcite by itself is a terrible lens because red light and blue light bend differently, so you have chromatic aberration. That means the eye's out of focus all the time. Well, what do? It turns out that if you radially substitute little amounts of magnesium for calcium, and this has to be a gradient from the center of the lens radially outward, that you actually can correct for chromatic aberration. And that shows you the power of evolution. If you had to nano-engineer a lens like this out of calcite, it would be incredibly difficult to do. But life, because of evolution, because of mutations, because of natural selection, has wound up with these perfectly engineered eyes. It's really quite astonishing. Okay, so that's the first stage of mineral evolution, a very qualitative story. We've learned that Earth's near-surface mineralogy is diversified dramatically, that all sorts of new pressure, temperature, composition regimes were invoked to make these new minerals, and that the biosphere was a major factor in the diversity and distribution of Earth's minerals. Those are really interesting findings, and I think they're important. It's also, this narrative of mineral evolution is a new way to frame mineralogy, and it's been used in education and engagement. I have to tell you that when I was a child, back in the 1960s, I used to go, and every month I would go into the American Museum of Natural History in New York, and I would spend hours in the Dana collection. This is the Morgan Hall of Gems and Minerals at the American Museum, and it arranged all the minerals by the Dana system, chemistry, structure. Each label would have the name of the mineral, the chemical formula, the crystal system, and the locality. And that's the way we organize minerals for more than a century. But mineral evolution is a new way of doing things. And here's the new Hall of Gems and Minerals at the American Museum of Natural History. It's a hall of the evolution of minerals. And it is so satisfying to me to go back to the American Museum and see the same specimens that I saw as a child arranged by the Dana system. And now the same specimens are arranged in this new way, telling the narrative of Earth history through the story of minerals. And it's not just the American Museum, the Vienna Natural History Museum, the Paris Museum, the Edinburgh Museum, the Houston Museum, the brand new Tucson Museum just opened this year. It's a mineral evolution gallery. That's the way they organize the minerals. So it's really I think, a more compelling narrative. Each mineral specimen plays a role in a play, a grand epic about the history of our planet. So there's still, though, and I'm sure you've noticed this is a very qualitative narrative, and we need to make things more quantitative. To do that, we need to harness deep time data and use the power of data-driven discovery. So this is part 2 of my story, and it's about a 10-year interval from 2010 to 2018 where we built the mineral evolution database. Now, the framework for this is an existing data resource called rough.info/IMA. Bob Downs at the University of Arizona, a very long friend and colleague of mine, built this. It's the IMA list of all the known mineral species. You can search by chemistry, you can search by structure, but now you can also search by evolution. So using Josh Golden and Alex Pires, who were graduate students at Arizona, and an army of undergraduates over that 10-year period, we built the mineral evolution database, brute force adding 200,000 mineral locality age data with all the metadata, the original source, reference source, and lots of other information. You can go and click on your favorite mineral and find out what the ages are known for those minerals. Now, we spent a lot of time focusing on the first row transition elements because these are economically important. Things like iron, cobalt, nickel, copper, they're common in Earth's crust, their chemical behavior is sensitive to oxygen, and they play really important roles in biology as well. So you make a plot like this, and what you're seeing here is a plot in which the horizontal axis goes back 1 billion, 2 billion, 3 billion, 4 billion years. And then in 50 million year bins, the number of mineral locality occurrences that we have in our data record. And so you also see they're colored by the oxidation state of those particular elements. And what we see here, there's a huge amount of information embedded in this, but let me tell you 2 main trends. The first has to do with the supercontinent cycle, because it turns out every 500 million years or so, Earth's continents come together in one supercontinent. Here you're seeing Pangea, and then the continent breaks up, and then at some point in the future, it will all come together again. And what we find is that there's an episodicity in the ages of minerals. This is best illustrated by the mineral zircon. That's a zirconium silicate. It always incorporates a little bit of uranium, so it's a natural clock, and zircon grains are incredibly durable. They last for billions of years. If you have an igneous rock that weathers away, the zircon grains will go into sediments. They'll flow down rivers. There'll be parts of new sand deposits, new sandstone deposits, and you can go back to rocks billions of years old. You can recover zircon grains and you can find the ages of them. And what you see are 5 main pulses, each associated with the assembly of a supercontinent. And we see the exact same thing in each billion-year period. The maximum value is always during the assembly of a supercontinent. So that's the first thing. Supercontinent cycle gives us episodicity in the formation of minerals. The second thing has to do with the effects of oxygen. So think about copper minerals. They can be native copper in the metallic state. You can have the intermediate oxidation state of +1 or +2, which is the most oxidized form. And here, Shauna Morrison and Simone Runyon have compiled all the copper data, colored them by their oxidation state, and you see a dramatic increase in the ratio of Cu2 plus to Cu1 plus minerals in the last 500 million years. There are many, many more details about this that I could share. We can show all of these data on skyline diagrams. Here, for example, are the various first row transition elements. There's a huge amount of information embedded in a plot like this. And we can actually do this for the entire periodic table of the elements. This is online. You can click on your favorite element. There's carbon and see how carbon minerals have varied through Earth history. So a vast amount of information to be unpacked and to learn from. And we can play all kinds of tricks with this. My good colleagues at the G-Plates program in Sydney, Australia, have developed plate reconstructions going back as much as 1 billion years. We can take one of those reconstructions. Here's the last 200 million years. And as you see the plates moving, you see little yellow and black dots. Well, those are copper and uranium mineral localities. And virtually every dot appears right near a plate boundary at the formation time. So this is a really dramatic way of learning about how minerals form and maybe predicting where to find new mineral deposits. Okay, so this is the Mineral Evolution Database, the MED. What have we learned? We see that minerals played a striking episodicity, age correlating with supercontinent cycles. What I haven't shown you in detail is that these different chemical elements reveal that each of those 5 supercontinents was quite different in detail. So it's not one size fits all, there's subtle differences. I've shown you that we've seen this change in the oxidation state of transition elements. What I haven't described today, and which is really fascinating, is that you can use the depth of formation of these minerals to understand not only the atmospheric oxidation, but also the rates of crustal oxidation. And that's incredibly important, for example, in the formation of ore deposits. So this is all information that's embedded in the data we've developed. And I think this is a very useful step. The MED, it provides this quantitative approach, but it really doesn't fully exploit the potential of mineral data. And that's why we've begun a new effort called the Evolutionary System of Mineralogy based on mineral informatics. It allows us to apply very powerful analytical and visualization methods and using these large and growing data resources that we're developing. So here's sort of a key idea of this talk. Minerals contain immense amounts of information. There are dozens and dozens of trace and minor elements. There are scores of different stable isotopes. There's structural defects of all different kinds. There's solid and fluid inclusions. There's morphology, physical properties, optical, magnetic, electric, elastic properties, petrologic context. Even things as basic as what vegetation occurs around minerals. I mean, there's all sorts of ways you can add information. And so this is part 3, mineral informatics. We began this in earnest in 2019, and it's an ongoing passion of ours, and it's probably going to be for decades to come, because this is the future of mineralogy. So what we need are data resources, and we already have. I mentioned the rough.info database. Mindat.org is an incredible database run by Jolyon Ralph, who has basically assembled all information on mineral localities and the coexisting minerals at those localities. Over 300,000 localities, over 1.2 million mineral locality pairs so far. And there's also just publications, Handbook of Mineralogy, Rock Forming Minerals, tens of thousands of original articles, all data that needs to be incorporated into data resources so we can move forward. And once you do that, it's amazing what you can accomplish. And I just want to take a few minutes as an aside to show you some of the new visualization methods that we can apply that have never been used in mineralogy before. Chord diagrams, used in biology all the time, but never in mineralogy. So this particular chord diagram, around the outside, there are 30 little arcs here, each one representing a different common cobalt-bearing mineral. Cobalt's really important because it's part of battery technology, modern electronics. It's a critical resource. And so understanding how cobalt minerals deposits occur on Earth is really important. And in this chord diagram, what you're seeing are coexisting pairs of minerals. Every known coexisting pair of cobalt minerals is shown in this diagram. Some minerals very commonly exist with others. Cobaltite very commonly occurs with erythrite, for example. But others are extremely rare, almost never occur. And so you can see all sorts of patterns, a vast amount of information displayed in a single diagram. Another kind of diagram is a clay diagram. This one's 72 by 72 matrix, so it has over 5,000 matrix elements, each one representing coexistence of the commonest chemical elements in minerals. So there are 72 essential minerals. If you want to know, well, how often does cobalt co-occur with arsenic compared to the crustal abundance? So you can estimate from crustal abundance how often minerals should occur, but you'll see hot spots like this one. So it turns out that cobalt and arsenic are associated with each other much, much more frequently than you'd expect just from crustal abundances. So there's 5,000 stories in this diagram alone. And we can also do this in 3 dimensions. Here's the 30 most abundant chemical elements in minerals, a 30 by 30 by 30 3-dimensional clay diagram, 27,000 matrix elements, each one representing whether or not the coexistence of those 3 elements together in a mineral exceeds probabilities based on crustal abundances. This is a lifetime of study in front of you, this one diagram, and you can manipulate, you can pull out individual sections and rows, all different sorts of ways of studying this. It's just an amazing way of approaching things. And here's my favorite. This is network diagrams. So a network, you're probably familiar with this in terms of social networks where you have a community of people, the European Astrobiology Institute, for example, but you have your own home institutions, you have your family and friends, you have your church, you have your school, whatever. You have many different communities and they overlap, and you can show the network of the people you know and who they know in a way like this. Well, minerals are the same way. Minerals have their friends that they hang out with all the time. They have other minerals that they never associate with. You can show this. Here are 37 different minerals, each represented by a circle. And they're the minerals that co-occur in igneous rocks. Those are the rocks that occur from a magma as it cools. And so there's a granite, a typical granite. There's an olivine basalt. There's a nepheline syenite. Indeed, every igneous rock that you've ever studied is embedded in this diagram, in this simple diagram. So there's a vast amount of information about mineral co-occurrences, about phase equilibria, about reaction series, all sorts of things. And we can do this in higher dimensions. These are called force-directed graphs, which means each interaction is like a spring, and so you can manipulate these. In the left-hand side, chromium minerals are colored by the way they form. Orange is igneous, green is weathering. In the copper minerals, here's the 243 most common copper minerals. Red are the sulfides, orange are sulfates, blue are oxides, and you see how very, very separate they are, the different formation pathways. There's so much information embedded in these diagrams, you can spend months and months studying them going in. You can do it in 3 dimensions. Here's Dan Humber's work on manganese minerals, 400 manganese minerals colored by oxidation state. So red is 2+, yellow is 3+, blue is 4+. You see a little cluster here. Those are manganese phosphates that occur in pegmatites. These are manganese minerals that occur at high pressure. You see they're mostly red, so they're reduced. But this hairball here, that's where all the oxidized near surface minerals are. By the way, hairball is a technical term in network science. So you could spend days and days and days studying this. It's just so amazing. And you can even do this in virtual reality. Here's Shauna Morrison walking into a 3-dimensional network of carbon-bearing minerals in blue connected to their localities in red. So that's network science. Okay. Back to the key idea of this talk. We can exploit these large and growing data resources to develop an evolutionary system of mineralogy. And that system reveals aspects of the coevolution of Earth and life. So what do we do that's different from IMA? First of all, some IMA species, we split them into several different natural kinds. In other cases, we lump a whole bunch of IMA species into one natural kind, and we also embrace amorphous materials, glasses, other non-crystalline materials, because those are really important in planetary history, but because they don't have a structure, the International Mineralogical Association doesn't recognize them. So splitting, think about diamond. To the IMA, diamond is pure carbon in the diamond crystal structure. But think about this, you have pre-solar diamonds. These form in the atmospheres of stars at very high vacuum, very high temperature by vapor deposition. That's different from a high temperature, high pressure diamond. Type 1 forms in an aqueous environment. Type 2 forms in a metal environment. So the inclusions are completely different in these 2 types of diamond. And then you have impact diamonds, if an asteroid hits a coal deposit, for example. And you have something called carbonado, where nobody knows what it is. It's a mystery. It's a sintered diamond of some kind. So these are at least 5 different natural kinds of diamond, even though IMA treats them as one species. Here's another example, apatite. You find apatite in meteorites, you find apatite in pegmatites with big, beautiful crystals, but apatite's also in the mineral in your teeth and bones. And I would argue that these are very different kinds of apatite. So single species, but multiple natural kinds. And finally, the world record pyrite iron sulfide, known as fool's gold, 21 different natural kinds that we recognize so far. Some from high temperature, some from low temperature environments, some from aqueous fluids, some from sulfide-rich fluids. Some of them are abiotic, but some of them are biologically deposited by microbes. And so these are different natural kinds. If we found pyrite on Mars, my first question would be, great, but what kind of pyrite? You know, if it's a high temperature hydrothermal pyrite, that's one thing. If it's a biogenic pyrite, that's a very different thing in terms of Mars. Now, in other cases, we lump mineral species together. The tourmaline group is very, very diverse. It has, I think, 37 different approved species now, and they vary because of ratios of elements. If you have a little bit more magnesium than iron, it's one species, a little more iron than magnesium, it's a different species. Same with aluminum and iron, or hydroxyl and fluorine. So when you have these colorful crystals, you're seeing chemical zoning. And in one of these crystals, you could have as many as 7 different IMA-approved species in a single object. We argued that that's a single natural kind. And this occurs on a very small scale. These are sub-millimeter grains where the core is one mineral, an iron-rich tourmaline called schorl. The outside is another, magnesium dominant called dravite, but it's just one crystal and it's one natural kind. So that's lumping. And finally, we embrace amorphous materials, volcanic glass like obsidian, coal, limonite, pyrolusite. These are all materials that James Dwight Dana included in his 1850 treatise. But because they don't diffract X-rays, they're not considered by the IMA. So that's something we need to change, because you think about Mars. I'm on the Curiosity rover team. We've been finding 50 to 70% amorphous phases in the soils of Mars. And how in the world can you possibly understand the history of Mars and its near-surface environment if you don't include those amorphous materials as part of the story? Okay, so how do we do this? How do we systematize this? 2 papers that came out in July of this year. The first one on the paragenetic modes of minerals. Paragenetic modes is just a fancy way of saying how minerals form, the process by which they form. And the second paper, as I've described, lumping and splitting. And this describes this whole process. So during COVID, I spent 6 months working typically 7 days a week, many, many hours a day, making this table, all 5,700 known minerals at the time when I did this about a year and a half ago. And then identifying about 60 different modes of formation, paragenetic modes of these minerals. So here we have this is basically a data resource that has 5,700 lines and about 60 columns. If you look in detail, each mineral is listed, and with a 1, you have that particular mineral is formed by that particular process. About 10,500 ones, that is combinations of a mineral and a process here, compared to the 5,700 mineral species. So a lot of different natural kinds represented here. And this allows us to make an evolutionary system, which is being published in parts in American Mineralogist. Part 1 is stellar mineralogy. And the way we do this is we have a binomial nomenclature, just like Linnaeus. The first part is the formation environment, in this case, a type 2 supernova. The second part is the name of a mineral, typically an IMA mineral like graphite. Here's an AGB star. It's a moissanite, that's a silicon carbide that formed in an AGB star. You can show this as a network, a bipartite network. Much of this work is done by our colleague Anirudh Prabhu at the Carnegie Institution. And what you'll see here is star-shaped nodes, which represent different ways that minerals form, different environments. So a type 2 supernova or an AGB star. and little diamond-shaped nodes, which represent the different kinds of minerals, graphite or moissanite. And every mineral is linked to one or more kind of star in this diagram. Every star is linked to one or more kinds of minerals. So here we have the 20 minerals and about 40 different modes of formation that we've identified. Now, how do we do this? I mean, how can you do this? It turns out we employ a data technique called cluster analysis, where you take these stellar moissanite grains, which can be extracted from meteorites, and we can analyze them. And we do the same kind of cluster analysis for pyrite. We can show several different types of trace elements in pyrite patterns that are formed. And we're building large databases so we can actually make these quantitative estimates of what the environments were where various minerals formed. Here's part 2 of the system. We looked at interstellar and solar nebular condensates, and you start expanding that network. So there's the solar nebula, here's interstellar clouds, and we have ice minerals here. So you're seeing the network expand. That's part 2. Here's part 3. These are the primary igneous condensates, chondrule minerals, getting us up to about 100 different phases altogether in this part 3 network. And you just see it keeps expanding. Here's parts 4 and 5. That's the impact minerals, the aqueous minerals, the thermal alteration. It just keeps growing. You can see this getting larger and larger. Part 6, which is now in press, shows the earliest Hadean crust. This is our estimate of what minerals might have occurred on early Earth. And here we've colored the network so that minerals that only occur with meteorites are shown in red. Minerals that occur in both meteorites and we think early Earth are shown in yellow. And the minerals we are predicting occurred on early Earth, but not in the meteorites, are shown in green. About 450 minerals in all. Interesting thing, there's the original stellar net. It's still buried in here. It has to be. We've just built around it, if you will, as mineral evolution goes on. And we think that this network is very similar to what we find on the moon, on Mars, excuse me. So Mars, it's very hard for us to imagine a mineral that occurs on Mars that's not in this diagram, or a mineral that's on this diagram that's not in Mars. That's a hypothesis. We're going to test it, but it just shows you ways we can think about Mars being maybe a stage 3 wet planet. And fast forwarding, because I'm not going to take you through the whole rest of this, this is the mineral network graph of all of mineralogy. This is the first visualization of all of the minerals known on Earth. And what you're seeing here is a bipartite network in which there are 5,700 little brown dots, each one representing a different mineral species. And there are about 60 different nodes that represent ways that minerals form. And so what you're seeing in the structure, there's lots and lots of minerals that form in only a single way. They're only known to form, for example, by igneous process here, or only known to form by a biological process over here. But there are also a bunch of minerals that are in the middle because they form by multiple paths. So they have to be linked to 2 or more of these nodes representing modes of formation. So this is an amazing graph. This could be a lifetime of work just studying all the different relationships among here. By the way, the colors represent different large groups. So these are anhydrous minerals, these are igneous minerals, these are biological minerals over here. There's a whole group of hydrated phases here. Lots of information buried with the colors. And we've learned some pretty interesting things. And I'm going to conclude by just telling you 4 of those things. First is that water turns out to be the principal driver of mineral diversification. On Earth, it accounts for well over 80% of all the known mineral species, probably close to 90% by water-rock interactions. Second thing is biology plays a major role in mineral diversity. Life can produce about half of all known mineral species, and more than 1/3 of all species are exclusively known through biological processes. This third conclusion to me is absolutely fascinating. Now think about this. There are a whole bunch of rare chemical elements in Earth's crust. Things like what are called the rare earth elements, the platinum group elements like platinum and rhodium and rhenium, arsenic, molybdenum, tin, lithium, boron, beryllium, cesium, There are 41 rare elements, and collectively, they represent only 1 in every 10,000 crustal atom. That's 1/100th of 1% of the crust. And yet those elements, one or more of them, are absolutely essential. They're required in 42% of all known mineral species. So these rare things play a disproportionate role in the mineral diversity on Earth. And I think what we're seeing here is the result of water-rock interactions, because water selects and concentrates these rare elements under different circumstances. And then it redeposits them in highly concentrated deposits. That's why we have cobalt deposits or cesium deposits or uranium deposits on Earth's surface. And finally, a highly speculative idea. The structure of this network, the topology of this network is different from the other ones we've seen, for example, for the moon or for Mars. And we're proposing that the diversity and distribution of minerals on Earth may itself be a planetary scale biosignature. This is a hypothesis that we're testing. We're fascinated by the prospects that minerals, not only this specific species, but also their patterns of co-occurrence, may reflect a biological world. With that, I want to conclude by just stating the obvious. We're entering this new age of mineral informatics. We're using multidimensional thinking. We're visualizing mineral systems in a new way, and these are leading to insights and predictions about the coevolution of Earth and of life. With that, I thank you very much for your attention. I hope there might be a little bit of time for questions.
Hi, Bob. Thanks so much
Yes,
for a wonderful. Can you hear me?
yes, I can.
Thanks so much for a wonderful journey, the journey of, let's say, of your passion for minerals. My question is a bit philosophical, and it's about the future of the knowledge, right? That we are building through these new approaches, right? And I recently read your PNAS paper with Carol Freeland, and I'm kind of in that. There was a bit of a tension there in between, like, what is historical natural kind and natural kind, right? And whether these are like complementary, or whether there's a kind of an alternative, completely an alternative way of looking at into what is a mineral, right? And when so the future, how do you envision the future? Something like a synthesis of the two more than, or how do you? Because when we speak about these alternative ways of classifying minerals, we're always like referring to IMA in some way, right? So it's like we are building on what is, what was supposed to be a natural kind, and we're constructing a new, more evolutionary or historical natural kind, but it's always in reference to the other. So what do you, is it going to be like an alternative way of looking, or is it going to be complementary to what we had? Or are there going to be more types of natural kinds? But in essence, there's no natural kinds. That's also something for life as well. No, every single living being is unique in some way. Like any particular mineral is unique in some way. So you could say there are no natural kinds, but humans need natural kinds to try to understand something around them. So how do you envision, let's say, the future of that knowledge? A synthesis of many things, or as alternatives ways of understanding?
So these are critical questions for us. First of all, I will say that we absolutely depend fundamentally on the IMA system. There is no way that we can move forward without the IMA classification. And that will be a baseline, I think, forever, because this idea of looking at the end-member composition and the idealized structure is just a conceptually fundamental way of tackling minerals. What we're doing is complementing that system by saying we can move to a next step. We can say, let's look at nature and see what the information inside each mineral tells us. We think that there probably are on the order of, if you're thinking about IMA species and then lumping them, but then also looking for these different kinds, we think they're on the order of 10,000 easily identifiable natural kinds of minerals. And when we say historical natural kinds, this is a fascinating aspect of this. And I won't go into too much detail, but you're correct that in biology, people talk about historical kinds, and it's been difficult because you have continuous evolution, and each individual shows different traits. It is conceivable, though, because there are specific historic events that lead to specific kinds of minerals, that minerals may be somewhat more amenable to identifying historical natural kinds. So that's something for philosophers to be thinking about. We'll certainly be working on this idea, but to me, that's really fascinating to think about. But we don't really, whether you call them historical natural kinds or even call them natural kinds or just mineral types or something, the words are not necessarily as important as remembering that pyrite can form in many different ways, and that knowing what those different formation mechanisms are tells us something about a planet.
Bob, this is Frances Westall. Thanks for a wonderful, wonderful talk as usual. I've got a more detailed question, going back to the very early stages of mineral evolution and so on. You're working with the Curiosity team on the mineralogy, and I have a question about the the feldspar minerals that have been found, the concentrations of feldspar minerals that have been found in Gale Crater, because I have difficulty imagining that these would come from granites, as certain people on the team have suggested.
Mm-hmm.
That they're on the Moon, for instance, feldspathoids or anorthosites are rich in feldspar minerals simply due to fractionation. I'd just like to have your take on this.
So most of the feldspars, the vast bulk of the feldspars that come from our analyses are plagioclase, typically intermediate plagioclases that are quite consistent with the basalt, various kinds of mafic igneous rocks. There is a small amount of sanidine, which is the higher temperature potassium feldspar, and to see potassium feldspars suggests that there's been some additional fractionation and differentiation, whether it comes from a granite or some other lithology. It certainly is a minor phase relative to the plagioclase. So far, I haven't seen anything in the feldspars that would suggest sort of a shocking petrologic implications that might be, the idea of there being granites in the sense of the granitic continents on Earth. I think no one really thinks that, but you can have late stage fractionation of silica and alkali-rich igneous lithologies, and we may be seeing some of that.
Okay, thanks a lot.
I'd like you to develop more this idea of biosignature from mineral, because usually the mineral have very broad spectral signature, and to identify something, you need rather sharp line. What about that?
So that's an interesting philosophical question. Some people say, is there a specific mineral species that is a smoking gun for life? And so far, we haven't come to that conclusion. And so what we're saying is maybe rather than any one particular mineral, which might be a biosignature on Earth, but is not necessarily a biosignature on some other world, that rather maybe it's the pattern that arises from the kinds of disequilibrium environments that life generates. So an oxygenated atmosphere, for example. So that it's that near surface disequilibrium that may be reflected in mineralogy. It might be reflected in atmospheres. It might be reflected in some other pattern that we can observe chemically. And this remains very much a theoretical idea, because it's doubtful that we're going to be able to apply it to any exoplanet for a very, very long time. But that's the kind of concept that we're following. We're looking for what essentially are large-scale disequilibria, so that you have coexisting in a near-surface environment many, many different pressure, temperature, composition regimes that are incompatible chemically with each other.
and you can find specific feature of this kind of process, because it's true that oxygen is considered as a biosignature, or a hint of a biosignature at least.
Yeah, so on Earth, certainly the presence of oxygen in the atmosphere is the major cause of disequilibrium in the near surface environment. And that's where you sort of have this tension where life is creating these gradients that then are reflected in mineral diversity in a near surface environment. So that's kind of the direction we're going. And we're also exploring the exact same kind of network topologies in atmospheric networks. So we think there may be something that is sort of universal about network structure and dynamics. But this is a very early stage, and to say much more than that at this point would be too much speculation.
Okay, thank you.
Thank you. It was a very, very interesting talk, especially for a non-geoscientist like me. And I find it intuitively very clever to start including things like coal, glasses, and stuff. But I wonder, where do you draw the line? I mean, wood apparently is not in your structure. Petrified wood as a mode of formation, on the other hand, possibly is in there. So is there a sharp criterion, or is it sort of more like intuitive?
At this point, we are grappling with this. We've actually talked about including wood. Any solid that's at Earth's surface, wood is a very interesting material, and there are other biologically mediated solids that might be included. So we're still grappling with exactly how to do that. This is a work in progress, and I'd be interested in other people's points of view. I mean, certainly coal, if we include coal, that's largely wood that's been processed over geological time through temperature and pressure. Do you draw the line someplace and saying, well, it's not altered enough? It's still a solid at Earth's surface, and it tells us a lot about planetary evolution, so we probably should include it.
Yeah, I was wondering also about like these polysaccharide biofilms that might be very crucial to the bioformation of certain minerals in bacterial colonies or something. But I can see that if you're starting from mineralogy, X-ray diffraction, that is stretching it quite far. But yeah, I'd be interesting to see how this develops, because I think it's a very, very ingenious way of looking at stuff.
So we include kerogen as it's found, for example, in meteorites and in many terrestrial environments, but then separate how far do we go? Do we look at different ratios of aromatics to other organic molecules? I'm not sure. Aromatic aliphatic ratios could be one way of using cluster analysis to say we have different types of carbon-rich material, condensed carbon-rich material. Insoluble organic matter, I think, has to be included in any sort of inventory of the important phases, condensed phases at or near Earth's surface. So again, a work in progress, and we love feedback.
One other very quick thing, what about anthropogenic materials like concrete or glass or so? I mean, it's not naturally occurring in a sense, but what qualifies as nature? I mean,
so we wrote a paper called On the Mineralogy of the Anthropocene, basically stage 11. And this has gotten a lot of attention. As you know, the discussions about whether we should have an Anthropocene epoch is highly politically charged. Some people say,
I know.
Humans are changing the surface. Other people say, no, it's much too soon to do that. But we include reference to all kinds of anthropogenic materials, but they're not yet recognized as minerals, and that's another whole thing. So yes, building materials, laser crystals, semiconductors, all these things that will be preserved in the geological record, persist for hundreds of millions of years, create a marker layer in the sediments. I don't see how you can not at least include them in some discussion, but how we deal with them in a classification system is yet to be determined.
If I may jump in again, sorry. This connects exactly with my initial question about how you foresee the future of the field as a synthesis. Because if if you're foreseeing it as a synthesis with IMA or what we know about physics, or what we know about, then you are not so free maybe to go all the way where you want. Whereas with these new classifications, because you are actually thinking about it as a way of converging with something, with some knowledge that we have that comes from solid state physics. I'm a physicist as well. And then there's something that you cannot leave behind related to what is a mineral from that knowledge that we have, the previous knowledge that we have. Whereas the type of things that you are suggesting now is like breaking completely and doing something like really alternative, so to speak, and don't giving a shit, so to speak, about what solid state physics has to tell us about what is a mineral or not. And so the last question, maybe this is the last question, it connects very well with and that's maybe making more precise my the question that I had originally. Right?
So we are certainly concerned.
Okay, there are two questions.
We're concerned with these questions, and I think that we need to, first of all, have tremendous respect for IMA and the people who do these kinds of, and then we have to ask what scientific questions are most important to us. And if the question has to do with the origin and evolution of life, I think that we can use and build in the IMA system very well. If we're talking about modern society and how humans impact the environment, then perhaps the IMA system needs to be amplified in a much more robust way. So we're at this point, I can be safe because we're only up to stage or part 8 of the system, which is metamorphic rocks. And then we get into biology when we get to part 10, that's the great oxidation event. And part 11 will be Phanerozoic biomineralization of some sort. And then we start getting into the tough question of where this goes from here. And I think we have to recognize that it's going to be problem driven. It's going to be which questions we're asking. If we're asking about the history of the Martian surface environment, we have to include amorphous materials. There's just no way out around it. If you're interested in the ways that humans are affecting the near surface environment, you have to include human-mediated mineral-like materials of some way. And whether that's included in mineral classification or classification of a different sort, we still have to grapple with that as scientists. And so this system we're proposing is highly flexible. It can incorporate many different kinds of materials because it's based on information of all sorts that relate to these condensed phases, not just an idealized chemical end member and an idealized structure.
Thank you. Thanks, Bob. Bye-bye.
I have two questions still on the chat. There is one by Jan. How about the origin of life in the geosphere? There are two key processes in life, metabolism and genetics. In the early days, it is the geosphere. Is the geosphere involved in the onset of one of these important processes for the beginning of life?
So our hypothesis, and this is not my work exclusively by any means, this goes all the way down to J.D. Bernal and Victor Goldschmidt more than half a century ago. So we certainly feel that minerals played important roles in metabolism in the sense that the cofactors of many metabolic enzymes look like tiny pieces of minerals, iron sulfur clusters. They include molybdenum or nickel or vanadium or copper. And I think that those connections have been made quite strongly. Also, in terms of genetics, you have to figure out a way to assemble genetic polymers. And one of the most effective ways of doing that experimentally is to use a mineral substrate such as a clay mineral, where you can oligomerize the various nucleotides. So it looks like minerals, when you think about early Earth, what did you have? You have oceans, you had atmosphere, you had rocks and minerals, and you had organic molecules. And how could minerals not have played key roles in those earliest processes of self-organization, jump-starting life? And so that's the hypothesis that we have and many other people have.
There is one question still by Kirsti Lopola Ruskeneme. Have you evaluated the rise of oxygen in oceans and the atmosphere from mineralogical databases since 2.5 gigayears ago? Another question, how about regional metamorphism that has changed mineralogy in
So these are great questions. And in terms of evaluating the rise of oxygen, I've got several papers that are either in press or published or in review right now that talk about exactly this. For example, we use manganese minerals to correlate the different kinds of manganese minerals, both with atmospheric oxygen and also the near surface oxygenation, the subsurface environment. We've used copper minerals for this purpose. There's papers that have looked at also trace and minor elements and their ratios, and many people have thought about it from this point of view. So minerals do preserve some of the information about the redox state when they formed, and you can see dramatic changes from the period about 3.5 billion years ago right up to the modern time. And I'd be if anybody wants, I can be happy to send you some references of work that we've done. Oh, and about regional metamorphism, that's the paper I'm working on right now. It's very interesting. When you think about when did different metamorphic minerals first come into the near surface environment, and this is a tricky part. You know, we're talking about near surface minerals. Well, certainly any lithology that's buried deep in Earth is subject to the high temperatures and high pressures that cause metamorphism. Regional metamorphism, for example, burying sediments, and this must have happened very early. So the question is, when did those high pressure metamorphic minerals, things like kyanite and sillimanite and the various kinds of pyroxenes and amphiboles and garnets that occur in higher pressure metamorphism, when did they first come into a near surface environment? We think that's probably associated with plate tectonics, because that's one of the ways the deep formations come near to the surface and then erode out. So you need to start plate tectonics, and that brings up the whole question, when did plate tectonics in its modern form really get going? Big debates about those ages, but certainly something that we're very interested in, and I think that understanding regional metamorphism from this mineral evolution perspective is quite interesting.
Okay, I see no more questions. I think we have already kept also for a long time for our questions. It was a very interesting session. Many thanks for all for coming, and special thanks for Bob for giving this presentation. And we will have our next seminar in 2 weeks, same time, same station. Thanks a lot to all, and goodbye.
Thanks to everybody. Bye-bye.